Right, the second part then. Finding the inverse of a matrix, not by the previous method, which was to follow the elementary row reductions, row operations to reduce the matrix down to its final form, but by using a technique involving what's called the adjugate or adjoint of a matrix, which is a rearrangement of it, replacing each of the elements by a submatrix, and the determinant being a number coming from the whole matrix, which determines whether or not an inverse exists in the first place. So, back to this one then. The determinant of A is this, which involves a calculation of multiplying the elements in any one of the rows. So you choose a convenient row, one with the smallest numbers maybe, but in particular any row that may have a 0 in it, or 2 zeros even better, or 3 zeros, in which case it wouldn't be anything. Multiplying each of these elements by what's known as its minor. That is, you knock out the row and column involving it, and you're left with a submatrix, and it's the determinant of that submatrix you multiply it by. So I'll just take the top row. So 1 would multiply this one, 1, 2, 2, 1. The middle one would multiply, take out that T shape, 3, 2, 1, 1. And the 2 would multiply, knock out that bracket on the side, 3, 1, 1, 2. But each of these has got a sign associated with it, which for a 3 by 3 matrix would look like this. But one that follows a fairly straightforward pattern. That sign, the sign of the minor, these being the minors, the sign is simply found by taking -1 and multiplying it by the position of the element. That's the row and the column added together. So that row 1, column 1, 1 and 1 is 2, so that's even. Row 1, column 2, 1 and 2 is 3, so that's odd, so that's negative. We'll jump to that one. Row 3, column 2, that's 5, that's odd, so it's negative, and so on. So you could use that in any size of matrix. So that means that's positive, that's negative, and that's positive. And then these little determinants of the minors are quite quick. Main diagonal minus opposite diagonal. So I've got 1 take away 4 is -3. I've got 3 take away 2 is 1, but multiplied by -1 is -1. I've got 6 take away 2 is 5, times 2, 10. So that means this comes to 6. So the determinant of the matrix is 6. Just like in the last example, there was a common fraction of a sixth in all the terms. The next part is to replace this matrix by a matrix involving all of its minors. So maybe I'll clear this space, although no, I'll just clear the space here. So I replace this matrix by all its minors, and I had the first 3 already. I'll just put them down again. So I've got space for the minors. I don't know if they're big enough for all of these parts. Why do you bother putting the brackets in first? You know they never fit. I should put them in afterwards. And also putting in the signs, because I want the signed minors. So that's plus, that's minus, that's plus, that's minus, that's plus, that's minus, that's plus, that's minus, that's plus. The signed minors. And I had the minors in already. So that for the first one, the minor is the little matrix that's left knocking out the row and column. So that's 1, 2, 2, 1. 1, 2, 2, 1. Had these already. Middle one knocking out the T. 3, 2, 1, 1. And the outside bracket 3, 1, 1, 2. Down to the next row, the 3 knocking out the row and column with 3. 1, 2, 2, 1. Middle 2. The middle one, so it's knocking out the cross. 1, 2, 1, 1. The 2 at the end. 1, 1, 1, 2. Down to the bottom row, knocking out the row and column with that 1. 1, 2, 1, 2. That'll be handy. The 2, so that's knocking out that row and column. 1, 2, 3, 2. And the last one, knocking out this 1. I'll left with 1, 1, 3, 1. It doesn't actually take that long, and there's no confusing arithmetic yet. And this next bit's just as fast. Because now what I want to do is just determine the values of each of these little minors. They're just little 2 by 2 matrices, 2 by 2 determinants. So that's 1 take away 4, -3. 3 take away 2, 1, but call it negative. 6 take away 1, 5. 1 take away 4 is negative 3, but call it negative, so 3. 1, take away 2, negative 1. 2, take away 1, that's 1, but call it negative. Nothing. And 2, take away 2, that's going to be nothing. 2, take away 6, negative 4, but it's the negative of that, so that's going to be 4. And 1, take away 3, that's negative 2, and it stays that way. And almost there. The last thing to be done is this then. Finally, to get the inverse matrix. To get the inverse matrix, you take this adjugate, or this adjoint matrix A, and divide it by the determinant of A. So to get the inverse, I'm going to do divide by the determinant, which I just rubbed out, which was 6. And the adjoint, or adjugate matrix, is this one, where every element has been replaced by its signed minor. The signed minor, also called the cofactor. Everything's been replaced by its cofactor, that cofactor being the signed minor. You take the matrix where everything's been replaced by its cofactor and then transpose it. So that I'll have turning the columns into rows or rows into columns, whichever you wish. So it's going to go negative 3, negative 1, 5, 3, negative 1, negative 1, 0, 4, negative 2. As before. The same result. You can judge for yourselves which was better. Was it better going through the elementary row operations, or was it easier to find this, the cofactors, replace them by the cofactors, transpose it and divide it by the determinant? Certainly if the matrix was bigger, it might be simpler using the elementary row operations, but it's not so bad for 3. And of course, when it comes to a 2 by 2 matrix, this is what you do anyway, because first of all you find that little determinant, you divide by it, and then you just flip it over, which is taking the transpose. So that's it done.